Hello, it's Keith here, and this is lesson 27 of the simple series of my 6502 assembly programming tutorials. Today we're going to be looking at sprite clipping again. Now last time we looked at tilemap clipping. This was where we used the tilemap to do simple graphics. You can see them here, but the problem with that is we can only move in 8x8 pixel blocks because we can't move in individual pixels. Now today we're going to be looking at an upgraded version. Instead of using the tilemap, this version uses hardware sprites. And this allows us pixel-based movement. So you can see we've got this lovely smooth graphic here, and it can go off the screen on all sides of the screen. So that's the example we're going to be looking at today. We're going to be looking at the upgraded hardware sprite version. Now what we're not going to do is we're not going to discuss the theory like last time, because I don't want to repeat myself again on the same system. So if you need to, after seeing this episode, to understand how the logical units work, or to see more details of the sprite clipping, please see the first 5 minutes or so of lesson 26 in this series, because that was already covered there. Anyway, let's go over to our source code and let's see what we're doing this time. So we've got this new example this time, and just like with the tilemap, we can't actually change the contents of the sprite memory outside of VBlank. So during our NMI interrupt handler here, we have a routine to transfer a sprite buffer. And we do this by simply writing the top byte of the address of the sprite buffer to memory address 4014. And this starts a DMA that transfers that memory, all 256 bytes of that memory, to the actual sprite VRAM. So that is all we need to do to actually get our sprite buffer into memory and get the actual sprites we want shown to the screen. So basically we have a sprite buffer of 256 bytes, and this is for the 64 hardware sprites that the NES is capable of. Now all of the sprites we're using today are 8x8 pixel sprites, and we're building these into a grid. The reason we're using the 8x8 pixel sprites is because my code is designed around sort of that kind of theory of 8x8 tiles. So we're using the same tiles as last time. There's no change to the tiles, it's just the sprite drawing code. So what we're going to look at today is the new upgraded code. Now the first thing we need to do is we need to actually know which sprite we're going to use next. Now in this example we're only showing one object to the screen, but if we were showing multiple, maybe we're showing multiple 16 by 16 pixel objects or something like that. Like in Super Mario, you'll have your turtle and your Goomba enemies. They're all made of multiple sprites, and we need to make sure we only use one sprite once on the screen, otherwise it will disappear. So we've got a variable called hSpriteNumber, which is the next available hardware sprite number. Now this will start at 0 at the start of our drawing, and so we're initializing it to 0 here, and then as we're drawing our object we will consecutively use hardware sprites to do so. So here is the start of our code. So our X and Y position before our cropping routine is stored in 0 page entries B and C. Our width and our height in logical units, which are 2 by 2 pixels. Each logical unit is 2 pixels. So that's our 48 by 48 sprite is 24 by 24 in logical units. So we're calculating that there. Our first tile is tile number 128. We're running our do crop routine, and that will set the carry if there's nothing to draw. Otherwise, we are going to end up here. And then we're loading in our hardware sprite number, and we're multiplying it by 4 because there's 4 bytes per sprite. Now actually we only use this routine once, and it's always going to start at 0, but just for completeness, in case we wanted to reuse this code, we're assuming that hardware sprite number might not be 0 when we run this. We're transferring that to Y, and Y will now be the offset within the buffer of the next hardware sprite we want to use. Now here is our main loop here. We're going to basically set all of the sprites along one horizontal line, then jump down and do the next line and so on. So what we're doing here is we're loading our Y position from C in the 0 page entry, and we're storing that to the first entry in the sprite buffer. That's the Y position. We're increasing. We're then loading the pattern number from IYL here, and we're storing that in the sprite buffer at the next position, increasing our position in the buffer again, moving to the next tile number. The example code here assumes that our Chibico graphic, or whatever graphic we're showing, will be consecutive tiles in all places. If you needed something more complex like a tile map to use repeating tiles or something, then you'd need to modify this. We will be looking at that later on in a future lesson as well though. Now we've then got a byte for the settings. We can do things like flip the sprite and things like that, but we're not doing that, so we're just writing a 0 to this entry in the sprite buffer. And then our final entry, the fourth one in the sprite buffer for this sprite, is the X position, so we're loading that from B in the 0 page entry. And then we're increasing again, because when this loop iterates again, we will be doing the next hardware sprite for the next part of our 48 by 48 pixel object, because of course we're chopping it up into 8 by 8 pixel blocks. Now the NES can do 8 by 16 pixel sprites, but as I say, it's not something I was using in this example. Okay, so we've done our first sprite, but we might need to do more sprites across the line. So we're now updating our X position, adding 8 pixels to our X position, and then we're repeating until our entire line is done. Now the X register in here has been loaded up here with H, which will now be the width in tiles or sprites with 8 pixel blocks basically. So that is that, and we're then just repeating until we've done our entire line. Once we've done our entire line, we're then restoring the B register, which is our X position that we backed up here. We're then adding 8 to our Y position, moving us down 8 pixels. And then we are skipping, if needed, we're skipping any sprites that are unused. Now this is used in the cases where our sprite is partially off the screen, because like in this case here, you can see half our sprite is actually gone and we need to skip that before we draw the next line. So that's what we're doing here from sprite H clip. We're just then repeating until we've done all of the lines. And then finally what we're doing is we're moving Y back, dividing it by 4 again, and that is now the hardware sprite number of the next hardware sprite that is free for us to use for any future sprite drawing on the screen. So that is our sprite drawing routine. Now there is something we need to do though, because of course there's no such thing as clearing the screen when it comes to hardware sprites. A hardware sprite will stick around until we get rid of it. Now this does cause an issue when it comes to the cases where our sprite was entirely off the screen, but it has now gone partially off the screen, because we will then need fewer sprites the next time we draw it. So we've got this function clear unused sprites, which will remove all of the extra sprites that we haven't used as part of our draw. Now I've just disabled this, and initially it looks like our graphic is drawing just fine. It is drawing just fine. But then if I go over to the left hand side of the screen, you'll see there's this weird kludge bin left over, and that's the unused sprites that are no longer needed to draw this very narrow chibi-ko. But as the chibi-ko comes back fully on the screen, those sprites have disappeared again, and this will happen to some extent on all sides of the screen, and that's because we're basically trailing sprites that are no longer needed as part of the total for drawing the chibi-ko graphic, because as I say, the chibi-ko graphic is a combination of 36 hardware sprites effectively. So what does this clear unused sprite function do? Well, it's super simple. All it does is it basically writes a series of zeros. It's calculating the offset within the buffer of the next free hardware sprite number, and it's just writing zeros to all of them until Y loops back to 0, so that we've basically filled all the remaining bytes in the 256 byte entry there, and so that's just zeroing them all out. Now I guess there is a bug in this, if you will. This isn't checking to see if actually all 64 hardware sprites were already used, so I guess maybe that's a slight mistake in my code here, but this example never uses all 64, so that's not going to cause a problem for today's example. But say this is a nice simple example to show you how to use hardware sprites. I mean, there isn't too much else other than what you've seen there. I guess the only other thing is we do need to write the correct value to port 2001 to turn on our hardware sprites. Now another option you can do is you can disable that strip on the left hand side. There was a black strip that was appearing before on the left hand side of the screen. You can sort of disable that, but then you will get this kind of effect where you'll see the amount of the left hand part of the sprite that is shown is varying as it's scrolling. But that is something that you may prefer to do, just depending on what kind of effect you want. But as I say, that is the other thing we need to do to enable this example. We're using the same tile graphics as before in this example. We're not using any kind of different format for our graphics, so we're using the same ones. Now the only other thing that has changed is the cropping routine has changed slightly. Now the cropping routine is converting the logical units to the physical ones, and it's also handling the crop. So here's the start of our cropping routine, and we'll go over this entirely again once more, same as last time really. But basically what we're doing here is we're zeroing sprite H clip. That's the number of missed tiles across the screen, so that's if our chibi-ko is partially off the left hand or right hand side of the screen. We're zeroing D and D here. Y is 0 throughout this routine. D and D are just temporary variables here in the 0 page. Now what we're going to do is we're going to crop the top of the screen. So what we're doing here is we're getting the Y position in the accumulator. We're subtracting the minimum logical unit, because there's basically bordering logical units around the screen in which we don't draw. You can see here, this is the sort of example here. So 64,80 approximately is the top visible left in logical units, and 192 by 176 is the last visible logical unit coordinate, and the invisible area is what we're going to use to allow us to crop parts of our sprite off. So that's how we're doing things. So we're subtracting the minimum Y visible pixel there in logical units, and if that doesn't cause a carry, then we don't need to crop anything off the top, so we're just going to skip. But if we do need to crop, we're negating this, and we're then comparing it to the height of the object, because maybe the entire object's off the screen. But if it's not entirely off the screen, this is now the amount we need to crop off the top. Now there is a change though this time. The code has changed slightly, which is why we're covering again. We need to effectively flip the bits of the remaining pixels, and this is to allow for the smooth scrolling at the top of the screen. Now if I disable this code here, before we were just loading a 0 in here, so if I just do that again, if we just do a TY to A here, which is loading a 0 from the Y register here, and I run again, you will now see we don't get as nice an effect. So now as I move up the screen, you can see we're basically moving in one tile blocks here. So we need to calculate a smooth offset, and that's those lines doing that. So there we've calculated the top of the screen. Now we need to do the bottom of the screen. So we're adding the height of the object, comparing to the height of the visible screen in logical units. If that's not caused an overflow, then there's nothing to do, but if it has, we need to convert this to an amount to remove from the bottom. Now we're calculating in sprite count, so we need to work in groups of 8 pixels. There's 2 pixels per logical unit, so we're masking to a number of logical units here, and we're seeing if that leaves anything left, and if it does, we're storing the amount to remove from the bottom in D. Okay, so we've now got the amount to remove from the top and the bottom, so we're adding those together and we're seeing if there's anything to remove, and if there is, we're negating it, adding it to the height, and then we're converting the height to a number of tiles, because again we're always working in 8 by 8 blocks. Now in some cases the sprite is partially off the screen and parts of it may be being drawn off the screen, but even in those cases there may be 1 or 2 pixels left on the screen that we do still need to draw. So we're updating our height there, and then what we're doing next is we're removing any lines from the top of the sprite, or the source data if you will, that are not going to be drawn at all, because we're not going to draw the sprites completely off the screen. It's just a waste, so we need to skip the source data in those cases. So what we're doing here is we're loading in from E, which is the amount to remove from the top, and we're converting this to a number of tiles. Now we're adding 4 here, and then we're logically shifting to the right twice. The 2 logical shifts are converting to a number of tiles, and we're adding 4 because we're basically drawing an entire tile almost entirely off the screen. So that's so that we can have just like 1 pixel at the very top of the screen, but of each sprite. But because of that, if the sprite is starting off the screen, we need to remove 1 extra sprite than we thought we might need to, if you see what I mean. So that's what we're doing there. We're then calculating the number of tiles in each line of the sprite, and we're adding that number multiplied by the number of lines to remove from IYH and IYL. IYL is the first pattern. IYH isn't actually used in this example, but just for completeness it is in there. And so that's what we're doing there. So that's cropping the height. We're now going to crop the width. So we load in the X position here. We're then subtracting the minimum visible X position, and if there's nothing to crop, we're going to skip over. But if there is something to crop, we're converting this back to a positive number, seeing if the amount we need to remove is the entire width of the sprite, in which case we don't want to draw anything. In all of these cases, we're jumping to all off screen here, which just sets the carry and returns, and our calling function will give up in that case. But if we're not, then once again we need to convert this to an X position to allow for the smooth scrolling as sprites are removed, and these are the calculations that we need to do that. So this is converting the X position to compensate for the missing sprite and allowing for that smooth movement as we're taking tiles off the left hand side. So once we've done that, we now need to do the right hand side. So we're now adding the width of the sprite, comparing it to the width of the screen in logical units, and if we need to remove anything, seeing if we're going to remove the entire sprite, and if we're not, we're storing the right crop here. We're then adding the left and right crops together. We're converting this to a number of sprites and seeing if there's any sprites to remove. If there are, then we're storing this in sprite H clip. This is the amount of sprites skipped, after each line draw. That's how much we add to the pattern number before we start drawing the next line. We're then converting this back to a number of logical units, negating this, adding it to the width of the sprite, and seeing if there's anything left. And if there is, then we're storing this as the new width. Finally, what we're going to do is we're going to update the first pattern number that we're showing to the screen. If we need to remove anything from the left, we've got to do this. So we're converting the logical units to a pattern count by just dividing it by 4 effectively. We're adding this to IYL. That is the first pattern that we're showing to the screen. Updating IYH, but again, as I say, this example doesn't technically need that. So now we've got our calculations in logical units, which are, remember, pairs of pixels. So 4 logical units equals 8 pixels equals one pattern width, or one sprite width, 8 pixels wide. So we need to convert this into something that we can use for our calling code. So what we're going to basically do is we're going to convert the X and Y position into a number of pixels by doubling them, converting from 4 logical units to 8 pixels. And we're going to quarter our width and height by shifting to the right twice, effectively converting from 4 logical units to 1 sprite wide or 1 sprite tall. We're then clearing the carry and returning, and that tells our calling code that there's something to draw. So that's basically all there's to it. As I say, if you need to know more, you want to see more about how the logical units work and the theory of the cropping code that I'm using, then please see the previous lesson, S26. That was Tilemap clipping on the NES. But as I say, go to my website, download the source code, and use it for anything you can in your own projects. And I don't think you can, but if you somehow manage to make a commercial project based on it, all the best to you. Now, we will be coming back to the NES, and we will be coming back to this kind of concept later on, and an example on tile maps and scrolling and more advanced things. It's a combination of effects. So we've got some sort of software tiles using the software sprites using the tile map, and we'll be hardware sprites and flipping and things. That's going to be coming a little bit later, so if you want to see that, please subscribe. And if you like the NES content, please like the video, because YouTube recommends based on likes, and I really need those likes. Anyway, hope you've enjoyed this today. Thanks for watching, and goodbye.